Hey, welcome back to the 3n+1 problem. Previously, we entertained the idea that the 3n+1 rule could serve as a full-blown computer. That is, you code up your program as some giant integer, stick that integer into the 3n+1 procedure, and then extract the program's output from the trace that 3n+1 leaves behind. Now, we don't know if 3n+1 can do general computations or not, and we certainly don't have a programming manual for it. So let's see if we could start writing a program manual. So previously we focused on loops. If we have a program that runs an infinite loop, we're going to have to code up that program as a start number for 3n+1. So what kind of number would you make if you wanted a loop? Well, we've been looking at that. For example, any integer of the form 3 to the x minus 2 to the x over 2 to the k minus 3 to the x would fall into a loop. But it turns out there are no integers of that form. And we don't know yet if there are any integers that loop, except for 1, 2, 1. So it's not clear how to implement a looping program. How about some simpler non-looping computation? How about a number that goes up 7 times and then heads back down? Well, there's a really cool theorem from Davison, 1976. It tells you how many initial up moves any number n is going to make before heading back down again. All you do is check the number of times that n plus 1 can be divided by 2. So take n equals 11. Then n plus 1 is 12, which can be divided by 2 twice. First to 6, then to 3. So we predict n equals 11 should go up twice before hitting an even number. And it does. Or suppose n equals 7. Then n plus 1 is 8, which can be divided by 2 3 times. And sure enough, we've got 7 going up 3 times. In 17, we know 18 is divisible by 2 once, so it goes up once. That means a number like 7, a number n that goes up 7 times initially, should be one where n plus 1 is a multiple of 2 to the 7th. So it should be of the form 2 to the 7th a minus 1, like 127, 255, 383, 511. So on. So let's test 383. Yep, it goes up 7 times before going down. Now for an n to go up exactly 7 times, we got to skip numbers like 255 and 511, which also go up an 8th time. So n is actually of the form 127 plus 256a. So right now we've managed to engineer a number that goes up exactly 7 times. We actually have our pick from an infinite set of numbers that do that. So how about another number that goes up 7 times, then down 7 times? That'd be a cool number. So after n gets pushed through the 3n+1 over 2 function 7 times, it winds up at m with this value. Skipping a few steps there. But you can tell m is a lot bigger than n. Now we want m to be a really even number that goes down 7 times in a row. So m is of the form 2 to the 7th b, or 128b. Actually, 128 plus 256b, to avoid m going down an 8th time. Now, to figure out which subset of n's leads to the kinds of m's that we want, we can substitute these restrictions into the general formula that takes n to m and simplify. And now, if we solve this, it's satisfied by a equals 81 plus 128c, and b equals this for any c greater than 0. So if a is of the form 81 plus 128c, we plug that in, and we find out that n is of the form 20,863 plus 32,768c for all c. So this is even better. We've engineered a set of numbers, n, that go up 7 times and then go down 7 times. Let's try the smallest one, 20,863. Yep, goes way up, then it goes way down. You can see this visually if we write this sequence top to bottom with each number in binary. It gets bigger here and then smaller there. Of course, after that, all bets are off. Okay, how about engineering a number that repeats that whole thing twice? So it goes up 7 times, down 7 times, up 7 times, then down 7 times. We can do that. After m goes down, it winds up here at n prime. And now we want n prime to also be of the same form that we have before. then it too will go way up and then way down. So I'll skip the details, but the result is that our starting n should now be of the form 308,728,191 plus this number times c. So the smallest number with the behavior that we want is a little bit over 300 million. And here's a picture of its 3n+1 sequence. It goes up, then down, then up, then down. Okay, that's enough engineering for one episode. We started with a simple desired behavior, and we found numbers that exhibit that behavior. But even for a very simple behavior like this, our start number had to be at least 300 million. So if we think 3n+1 can do complex computations involving loops and if statements, well, the required start numbers are going to have to be way, way bigger than 300 million. So we get a lot more engineering to do.